Alright, so in the last couple videos, we talked about random variables whose outputs or whose potential values are numerical values, right? We're talking about things like weight or changes in weight, um, money, that sort of thing. And so what we're going to be discussing now is what happens when our random variables are categorical and not numerical, and what sort of inferences we can make about categorical data. So let's start with the most classic example and potentially maybe the most relevant. So let's say Leslie Knope is running for office. Uh, she posed her campaign wants to determine what proportion of people maybe want to vote for her, right? And so uh, the campaign pose some people to measure the support, right? And based on these results, they want to know, does the proportion of people who support her does the proportion of people does the proportion of people who support her exceed half or 50%? All right. And so let's go ahead and set our alpha to be the standard 0.05. And this statement by itself is gives us a natural null and alternative hypothesis, and that is that the proportion of people who support her might be a half, and the alternative here is that the proportion of people who support her are greater than a half, right? Okay, and of course, at this stage, we can't actually do any hypothesis testing because presumably what we're missing here is what does some people mean, right? Like how many people are polled, because that matters, right? That's our sample size. And what the sample proportion is, right? Out of those people we poll, what percentage of them support Leslie Knope? And so we'll get to all of that. But uh, the way we want to think about this theoretically is, so in Pawnee, Indiana, uh, it has a town whose population is, we're not sure, let's just say NP for Pawnee, that's some number, and some proportion of them, let's say PP, is supports Leslie Knope, right? And whatever those numbers are, that means that on voting day, the proportion of people who vote for Leslie Knope, we can think of that as a binomial variable, right? With parameters N and P. And presumably Pawnee, Indiana is a big enough place where we can approximate the binomial variable with a normal variable, right? So what's binomial is the total number of people voting for Leslie. And we can approximate it with a normal variable because n's big, right? And recall that the parameters of the normal variable are going to be, it's gonna have average value, uh, whatever proportion of people support Nestle times the population, that's gonna be the mean, right? And then the standard deviation is gonna be the square root of n p 1 minus p, right? But if what we're caring about is not the total number of people who support her, but that's not so important, right? Because if I say, you know, 500 people support Leslie Knope, that doesn't tell you anything about whether or not she wins or loses without knowing how many people voted, right? So the raw numbers here are not important. It's the proportion of people who do X, Y, or Z that actually matters. So why don't we go ahead ah, and compute the proportion and when we compute the proportion of people for Leslie Knope, all we're doing is taking the total number of people voting for Leslie Knope and dividing it by how many people there are, right? So all I'm going to be doing is dividing both of these by the total number of people. And so the proportion of people voting for Leslie Knope, that's also a normal variable with average value, the proportion, and standard deviation. Well, since we're dividing by n in this case, it would be the square root of p times 1 minus p over n. And so, of course, the question is, well, what is p and what is n? And we don't know, right? We don't necessarily know what either of those things are. But as usual, when we take a sample, we can make an estimate for both of those things, right? And so, just like every other hypothesis testing case, what we're going to do is we're going to assume the null here, right? We're going to assume the null hypothesis, and then we're going to see how likely it is that we get the results that we get. All right, so I'm going to go ahead and I actually made up this little thing here, which will allow me to take a random sample. So hidden in this folder is the actual proportion of people who would vote for Leslie Knope, and that's hidden because we don't know what that is. Let's say we take a sample of size 50. So we go ahead and generate a sample of size 50. Um, and so here I would say that n is 50. And my sample proportion is out of these 50 people, how many of them vote for Leslie Knope? And in my sample proportion, that's 66%. And so if you recall from how we would have done something like this with z hypothesis variables, because we assume the null, we're going to assume that our normal curve here has a mean of 50%. And that comes again from assuming the null hypothesis, right? And then the p hat here gives us a value for the standard error. The standard error, again, coming back to this slide, is going to be this thing here. We're going to use as an estimate for the standard error 0.66 times 1 minus 0.66, which is 0.34, all of this over 50, right, which is the end that I found, right? So we can kind of say both P determines those two values and 1 minus P determines that value. Then, of course, our 0.66 is here, and then we can compute a p-value, which is that area, right? And so I'm not going to belabor all of this stuff because we've already done this over and over again in chapter 4 in various forms. The only difference is how we compute standard error because we are taking a modified binomial variable, right? Uh, to figure out what percent or proportion of people vote for Leslie Knope. But uh, let's go ahead and figure out what something like this, what the p-value should be with our proportion hypothesis testing calculator. So let's say that n is 50, and in our sample 0.66 percent of people supported Leslie Knope. We want to compare that to 50%. We had an alpha of 0.05, and uh, our alternative hypothesis is that the proportion of people who support Leslie Knope is greater than P naught, which we said was 0.5, right? We want over half the people to vote for her, and that would make her the winner come election day. So if we click on that, then what we get is a p-value, in this particular case, of about 0.012. Let's be a little bit more precise, 1825. Right? Which is definitely less than 0.5, which is what we said our alpha was going to be. Right? And so we can then reject the null hypothesis. This is strong enough evidence to say that yes, she probably has over 50% of the support. If I wanted to know how much support she had, well, let's say I wanted to find a 99% confidence interval. For proportion of support, well, similarly to how we would have done this with z variables, 0.66 was our point estimator, right? Let's go back here still. 0.66 our point estimator. Our standard error is still square root 0.66 times 0.34 over 50. And then we want to go out so that that's 99%. And so you can go ahead and use that, do that in the inverse norm calculator if you want, but all we would have to do here is unclick that because we're not hypothesis testing, toss in our 1%, and then click on a confidence interval here, right? And then we can safely say that there's a 99% chance that her level of support is between 48.74% and an upper bound of 83.26. And so this might be a little weird because we look at this and say, hey, didn't doesn't this interval here include 48%? And that means that 50% is somewhere right here. So that there's some chance then that she actually has less than 50% support. And yeah, that's correct. There is some chance that she has less than 50% support, and you just sampled a group of people who happen to disproportionately support her. And that's not inconsistent with what we found because remember, 99% is a much stricter and higher threshold for accuracy than the alpha equals 0.5 we're looking at here, right? And so, uh, even to compute the confidence interval, we notice that we have to lower the alpha down to 1% in order to find this confidence interval. So a 99% interval demands more certainty that the candidate will win. And while hardly there's hardly any chance, looking at this curve, that her level of support is less than 50%, it's not none. So it can't be ruled out if you use a 99% confidence interval that she doesn't have popular support. All right, so hopefully that's helpful there. Um, I just want to point out that you can do something similar. So let's say that something similar to what we've been doing with z and t variables. So let's say um, you interview uh, see you out of 30 Pawneans, let's say 18 support Leslie, and then out of, let's change colors slightly, out of 40 Egotonians, let's say 22 support Leslie. Is there a difference in support? Uh, alpha B 5%. Okay. So let's split this up into our two different populations. Out of the Pawneans, our first sample here, we have a sample size of 30, and the sample proportion here is 18 out of 30 Pawnean supporter, right? Out of the Egotonians, we have a sample size of 40, and then out of them, 22 support Leslie. And we want to know if there's any difference in between how much Pawneans versus Egotonians support her. So we have our null and alternative. Our no is that there is no difference, right? And then our alternative would be that there is. And so we note, by the way, that we could compute a standard error for both of these populations, right? In the same way we just did a few slides back, right? Using this sort of technique here. And then the standard error of the difference is going to be the square root of the individual standard errors squared. Uh, and this will allow us to construct a normal curve again, assuming the null. So assuming the null, and then our standard error here is the square root of, well, let's see, looking at our first population here, we have 18 out of 30 times 12 out of 30 over 30. And then we're going to add that to 22 out of 40 times 18 out of 40 over 40. And we're taking the square root of that whole thing. And then the observed difference between the proportions is, I'm going to go ahead and just pull up a new blank graph here. 18 out of 30 minus 22 out of 40 is 0.05. So it doesn't seem like it's very different. That's our point estimator here. And so our p-value, as before, is the area of these tails, right? It's this area plus this area here, just like the two-tailed proportions in the other chapters. All right. And again, rather than painfully compute these numbers, compute a standard error, and run that whole thing through a normal calculator, we could just go to our hypothesis testing here. And let's go ahead and pull one up. Hypothesis testing proportion to variable, because we have two of them. Our first sample had size 30, out of which 18 out of 30 supported Leslie. The second sample was size 40, out of whom 22 supported Leslie. We want to compare that to a null of no difference. Alpha we said was 0.5. And our alternative hypothesis is that the difference is not 0. And so given these values, we end up with a p-value that's absurdly large, 0.6746, definitely greater than 5%, right? And so what that means is that if we assume there's no difference between Pawnian and Eagletonian support, then there's a 67.5% or so chance that we would see results like what we just saw. And so that's pretty likely, right? That's over 50%. It's definitely over 5%. So that means there's no evidence that suggests the null hypothesis is wrong. We have to accept the null. All right, So, one thing of note, in order to do any of this stuff, there have to be some conditions you have to meet. Um, so first of all, in order some conditions for being able to do this are all the samples have to be independent. Now, in the problems that we'll work on, this will be a given assumption, but it's really the most difficult thing to do in real life. Um, Especially if you're doing things like polling, you can't just walk into a room and just ask people who they're going to vote for. People might feel subconscious about their choices, and if other people say things, they might want to follow along, and that taints the independence, right? And it also matters like exactly how you conduct the interval, the or conduct the sampling. Like if you walk into Leslie Knope's campaign headquarters and did this poll, that's very different than if you were to go to like a college dorm or a union office or any type of scenario like this, right? And so this is a tricky problem, and in the courses within your majors, there'll be uh, some discussion of how to achieve this. But mathematically, one of our conditions is that all the samples are independent. And then the next condition is the rule of 10. And the rule of 10 basically says that your n needs to be big enough so that, and your sample needs to be big enough so that at least 10 people say yes to whatever it is that you're asking them, and at least 10 people say no. If you don't have at least 10 for each, then the proportion is too skewed one way or the other uh, to guarantee that the normality of the sampling distribution. So you need to get an n large enough so that at least 10 people are saying yes and 10 people are saying no. And mathematically, what we can think of this as is 10 successes. That's the same thing as the number of people that you sample times the proportion of people who say yes has to be at least 10. 10 failures means of all the people you sample, the proportion who say no, that also has to be at least 10. So you need to be able to check off both of these in order to invoke the techniques that we have so far in this video. All right, so that is proportion hypothesis testing and confidence intervals. I hope everyone enjoyed that, and I will talk to you later.